In this video, I'll show how to generate conformers necessary for the simulation of the spectrum of a molecule. Here we're using an example where we have a 5-membered ring containing a nitrogen, and there is an isopropyl group attached at the nitrogen and a hydroxyl group attached at a different position on the ring. It's a chiral molecule, and we can see the chiral carbon labeled here as R. This would be the R stereoisomer. This particular molecule has a great deal of flexibility. That is to say, there are bonds which can rotate. This one in particular, the nitrogen-carbon bond here, this group, the isopropyl group, can rotate into 3 different positions. The hydroxyl group also can rotate into 3 different positions. And finally, the 5-membered ring can flex in and pucker into 2 different configurations. 3 times 3 times 2 gives us 18 total conformations for this molecule. So if we were to properly model any property, such as the IR spectrum or the VCD spectrum, we would need to do that calculation on all 18 conformers and then weight the results according to a Boltzmann distribution. This Boltzmann weighting can be done by GaussView at the conclusion of the calculations. I have a video describing that as well. Here we're focusing more on just generating the conformations. So let's start with the isopropyl group. We see that if we look end on the bond that's rotating, there's a hydrogen sticking down, and then the 2 methyl groups are sticking on either side of the bond. And basically this hydrogen can occupy the same position as the methyl groups. And so this is the first configuration, but we can rotate and put it here, or we can rotate and put it here. In order to generate here's the first conformation for that isopropyl group. If we want to change it, we move the dihedral angle. So there's a dihedral angle tool that's up in here in the control panel that's just to the left of the question mark with a ruler. Modify dihedral. And we can click on one of the carbons of the ring, and the nitrogen, and the carbon, and then the hydrogen. And we do that in that order so that the bond that's rotating is the 2nd and 3rd selection that we make. And the 1st and 4th are the things that we're twisting with respect to that bond. There's a smart slide box that comes up in GaussView. We'll choose to fix the atom 1, which was the carbon of the ring, and we'll rotate the groups present at atom 4. And we can actually slide this and take it through 180 degrees back to the beginning. So 180 is the first conformation. If we go to the position that's staggered there, we get the 2nd position. And then if we turn it all the way to there, we'll get the 3rd position. These angles don't have to be exact. We're just getting a starting point for the calculation, and the calculation itself will optimize to the exact dihedral angle. We're just trying to turn it there and there to generate the conformations due to the isopropyl group. Likewise, this hydroxy group that's on the other side of the molecule, it can adopt several different conformations that are staggered. So if we look at the hydroxyl group, we can choose the hydrogen here, the carbon here, the oxygen, and the hydrogen. Again, remember the rotating bond is the second and third atoms selected. And we'll fix the first atom and rotate the groups again. And you can see we can take this hydroxy group through its entire paces there. Let's start it at 180 as the first one. We could save that out. And then we'll twist it to about right here, which should be about 60 degrees. We can even type 60 degrees in here if we want to put it exactly at 60. And then the other one should be at about minus 60. 180, 60, minus 60 for this rotating hydroxy group. And now we want to look at the 5-membered ring. We said this can pucker one of two ways. If I align these two carbons, you can see that we've got a carbon that's down in front and the carbon that's up in the back. But we could have the carbon in front up and the carbon in back down, and that will flip those two. We could try to do that by moving the angles around, but it's going to be difficult. So instead, there's a trick that we can do in this case, and that is we can mirror invert the entire molecule and then just move the hydroxy to the other carbon. So that's under Edit, Mirror Invert. Of course, this has temporarily made this the S form until I move that hydroxy back to the other carbon where it was. I can simply delete it here, attach a hydrogen there, and add the hydroxy there. And now I again have the R isomer. I have not changed the stereochemistry, but I have changed the ring puckering. That's a little trick you can do for this 5-membered ring. Okay, so we've done the explanation and demonstration of how to generate the conformations of a flexible molecule. We use the dihedral angle tool, and we can do some tricks with flipping rings if we have to do that.